Thank you, Adrian and Celia, for inviting me. I'm going to talk about the last decade of research at Varved Lake Zabinskie, and this talk is going to be divided in two. Did I turn off my camera? No. Okay. So it's going to be about the decade at Lake Zabinskie, and I'm going to divide it in two. So the first part is about actual research that was carried on during this last decade, and the second part is about the research that is done on the data from the last decade. So the first part is like briefly going through what we done, so to establish some kind of background and just to look back at what was done once we reached this decade. So that's it. On the beginning, as it used to happen previously on Varve seminars, I want to talk all of the people that were somehow involved in Lake Zabinskie. So either as co-authors, co-investigators, or just not just, but helping us in the field, in the analysis, and in whatever way with good word and so on. So I don't think that this list is complete. I tried my best. Obviously, during the decade, there has to be a lot of money involved to carry on for such a long time. So I'm not listing everything, but those two sources on the bottom of my of the slide are like the most recent dealing with Lake Zabinskie. So one is from Polish National Science Center, and the second one is from Swiss National Science Foundation. So we need to thank them also. So there is a why Lake Zabinskie? So it goes back to the gap, which is Central and Eastern Europe. So there is still used to be and still is a need to fill the gap of the paleoenvironmental climate reconstructions, mostly in this area of Europe, which is densely populated. And if we have something, it's mostly from the tree rings. So it would be good to have something that is based on lake sediments. And for quite a long time, Lake Gościąż was the only Varved site that was explored in Poland. It was the Varved sediments were found like in 80s of the last century, and then not much was done regarding the Varves in Poland, which is surprising because just across the border in Germany there were obviously Varved sediments and a lot of them. So at some point, I guess people like Wojtek Tillman had to ask themselves, well, there has to be something in Poland also. So I can only speak on behalf of the Gdansk group. So they started to work with Bernd Zoliczka, and they found, and the Bremen group, and they found that there are actually quite a few lakes with Varved sediments in Poland, and they are worth exploring in different ways. So then, with the help from and establishing of the Swiss, Polish-Swiss program cooperation with Martin Grosjean at the lead of the Swiss side, they started Klimpel project, which was aiming for the climate reconstruction, paleoenvironmental reconstruction for the last 1,000 years. And they seem to look for the right site to do this high resolution reconstruction. So basically for this kind of thing, you need to have good Varve quality, obviously high enough sedimentation rate. So there is actually signal being recorded in the sediments. And there is also material that you can clearly and basically subsample. And it's good to have rich and variable ecology in the lake. So there is a lot to get the data from in terms of paleoecology. And it is good if it's remote, especially if you are interested in natural variability. And one of those lakes was Lake Zabinskie, and it was finally chosen to be investigated. Lake Zabinskie, like most of the lakes in this part of Poland, is of post-glacial origin. It's a kettle hole, which is relatively deep and medium in size. It's a hard water lake, flow-through lake, which is clearly and highly eutrophic at the moment. What is important for us, people dealing with Varved sediments, is that it's thermally stratified and at least seasonally, Hypolimnion is anoxic. And that means that for prolonged periods, Lake Zabinskie is in fact meromictic lake, meaning that together with the high primary productivity and the part of the world that we are in, it's very good site for the formation and preservation of Varved sediments. And these sediments were basically studied throughout the decade. And that was the coring team in 2011. So basically, I think that you can, you know, some of those people. And then the 2011 was preliminary coring, and then in 2012 the long core was retrieved from Lake Zabinskie with help from Bremen and from Poznan. So also familiar faces at the time. And we have core, and we also have at the time established monitoring setup, which I'm going to show you later on. It's a surprise how it looks right now. But with the monitoring, what is important that after 2 years, Ala took this endeavor to characterize the water column dynamics, what is happening in the lake. And after those 2 years, we can clearly see that, especially that obviously temperate lake is thermally stratified, but what is important is the oxygen concentration that is changing over the year. Basically, Lake Zabinskie could mix fully twice, once, or never, not never, but not in a given year, meaning that the mixing regime, at least right now, is really complicated, and that has to influence the Varve formation. And also, after the ice breakup, almost every year, there is a high and intensive diatom bloom happening. So at this point already they knew, because I was not involved, right, what is happening in the water column, and also they knew what is happening in terms of modern sedimentation, because they gathered the first data on from sediment traps. And they could clearly see that the Lake Zabinskie sediments are forming in seasonal pattern. There is some kind of seasonality. And after comparison with the sediment core, we can clearly see and say that indeed sediments in Lake Zabinskie are varved. They are annually laminated. And one of the striking features of those sediments, at least at the top of the core, is that there are multiple calcite layers occurring throughout the given Varve year. So at this point, it's established that Lake Zabinskie sediments are varved. So when you have varves, you can go on and do the most fundamental job, which is creating chronology. And that was another task that Ala took on, leading the paper and this research. It was about devising new way to do the chronology, construct the age depth model, and also assess the uncertainty. And it was based on the 3 independent counts, then comparison of those counts, meaning that if everyone, 3 different people agree on the Varve, the chronology is just extended by 1 year. If one of the people is not recognizing the Varve, then the chronology is once again extended by 1 year. However, the negative uncertainty is being bumped by 1. And in the opposite direction, if only 1 person sees the Varve at given depth, there is no change in the age of the sediments. However, the positive uncertainty is rising by 1. And afterwards, all of that is integrated and leads us to the creation of age depth model, which looks exactly like this for the last 1,000 years. And it's what is striking, at least for me, that it's so precise and that it fits so good with the radiocesium, which is independent from Varve counting, and also with the Aschia tephra, which was found a little bit later on. And also during that time led to 10 dating models, and chronology development was tested. And as it's very often, it's good to use simple terms to get the really good results. So that's how the chronology for the last 1,000 years look. And then we could move on to the 2,000 years. So that's something that I took on. And we extended the core to be 6 meters long from the 3 meters. But only extending chronology would be not enough, especially for a PhD student. So I also tested 3 different methods to assess the uncertainty of the Varve chronologies. So one is popular, where you uncertain year is just a half a year for chronology, and another half is uncertainty. Then you count section, like thin section, multiple times, and then calculate the standard deviation or other measurement and use that as a uncertainty measure. And then the approach that was previously proposed for Lake Zabinskie. And based on that, I created 3 different age depth models, which basically look almost the same. if you don't look at the numbers. And also it was validated by radiocarbon measurements. And I was so happy to find this small cone exactly in the last sample of my subsampling for this core. And it was huge and provided really good anchor for the bottom of our core. And then afterwards, when everything was compared, it seems that our, let's say, method C, seems to produce the most fitting age depth model, but also shows the more probable course of the uncertainty direction. Then we went a few centimeters down also when Gosia Kinder was looking for the cryptotephra in Varved sediments in Poland. And so we extended the sampling by a few centimeters, but first we found White River ash tephra from Mount Churchill, Alaska, which is fitting perfectly, I would say, in the chronology. And then two tephras from one from Iceland, Glengarry tephra, and one from volcano Furnas from Azores, which are fitting in the bottom of our chronology. And this is like an example that Varved lake sediments are a really good way to date tephra layers, things that are like very distinct, and it's good. It's a good constraint on the age of those sediments, and also tephra is a good constraint of the age of the sediments, but also sediments are good to constrain the age of the sediments between the sites. So it's like feedback one from one to another. And then we were like, okay, we need to go even further deep, and we tested MICADAS radiocarbon approach. So MICADAS is a mini carbon dating system that is used for very small samples because it's using gas ion source that bypasses graphitization step for the AMS measurements. So we did it for the last more or less 9,000 years. With 31 samples measured with MICADAS and 17 samples measured with typically with graphitization. And then we also went with the model of simulated models of different sampling density and different amount of carbon that would be in given sample. And after that, we could suggest that it's okay to start with low dating density for radiocarbon, because more often than not, we don't have much material. It's luck to find some micro remnants and so on. So it's okay to start at low density, then fill the spaces where the highest uncertainty range is observed. And if it's necessary, then use this microdose carbon dating system MICADAS just to date more samples, even though they would produce a little higher uncertainty, but it's better to have them dense rather than very big samples that are very sparsely dispersed over the age depth model. And then, just to be on the good side, we extended this chronology for the entire profile, and it's most of the Holocene. It's 10,800 years, more or less. And that's the final chronology that would be used for some of the reconstructions in Lake Zabinskie, and it's the base of the core is also dated with radiocarbon. So what were we have chronology, so what were the examples of reconstructions that we did or were done on Lake Zabinskie? For once, one of the better looking, I would say, is the erosion intensity as an answer to the land use changes over the last 1,000 years, where microfacies data, micro XRF, and pollen data were used together. And at this point, it could be clearly seen that the human-induced land use changes were reflected in the intensity of the erosion and the delivery of the detrital material. That was the first indication of the land opening influencing the lake mixing regime and the possibility of using iron-manganese ratio as a tool to reconstruct hypolimnetic oxygenation. And finally, Varve structure reacted rapidly to the changes of detrital input intensity. So having that in mind, we went for 2,000 years. And even though these are biochemical Varves, we tested grain size distributions of those sediments and then we also decomposed those grain size distributions with an end member modeling approach. And it seems that even these are mostly organic composed varves, still grain size is useful. This kind of data is useful and also traces those mentioned before changes that were caused by human activity in the catchment. And for end members loadings, it's really striking that this kind of data coming only from grain size, which is independent from the geochemical data, obtaining the geochemistry, it seems that at least some of those end members are highly correlated with the geochemical data, especially this end member number 5, which is correlated with total inorganic carbon concentrations in Lake Zabinskie. So even though it's used mostly for clastic sediments, still grain size data is could be useful for biochemical varves. Then going on also for what was proposed before, we tested iron to manganese ratio for 2000 years as a response to the changes in the catchment. And it seems that even though the trityl component is more or less is a source of those elements, their burial in the sediments is redox driven, meaning that at least in case of Lake Zabinskie, iron to manganese ratio is useful ratio and it could be used in that way. And takeaway message from this exercise is that lake sheltering indeed plays an important role in driving the mixing regime changes for Lake Zabinskie. Basically, if there are more trees, the lake is not mixing, at least not mixing completely. If there are less trees around the lake, holomixes, complete turnover of Lake Zabinskie is possible. And then we extended it even further for entire Holocene. So we used still XRF data, but we also used hyperspectral scanning data. 2 proxies. One is total chloropigments A, showing the productivity of the lake, and second one is bacteriophyllophytin A, showing meromictic periods or anoxia. And what is important that it's most of the time Lake Zabinskie was naturally anoxic lake. However, in the last 2,800 years, it started to become heavily variable in terms of mixing regime. And what was important for me, indeed, in this period between 7th and 15th century of Common Era, meromixis was very strong. It came back to Lake Zabinskie and it was just in agreement with iron to manganese ratio. And then since 15th century, primary production and mixing regime became heavily impacted by human activity. And once again, we proved using pollen data that the primary control on lake mixing is the density of forest cover surrounding the lake, but also it's always at least a bit of climate driven. When we are talking about the primary production, there is also a little bit older reconstruction for 100 years based on chloropigments also, but with a slightly older technology. And it was used to reconstruct the springtime temperature. However, for me and for what I'm going to show you later, the most important part is that the spring mixes controls chlorophyll air concentrations in the lake. Then using chrysophytes, we also did some reconstruction on the wind speed in the and the activity of wind mixing, exerting control on the calcium ions in the Lake Zabinskie Hypolimnion. And this is also important because it seems that wind mixing controls calcite precipitation in Lake Zabinskie, at least to some extent. So it is also going to be important later on. And chrysophytes also were useful to reconstruct the number of days with Hypolimnion temperature below 4 Celsius degrees, and it was done over the last 1,000 years. So there is a significant relationship between chrysophytes assemblages and this climate variable. Even though land use changes were important in the lake, especially most recently, this parameter and then chrysophytes were mostly independent of that impact. And there are some clear shifts that are pretty much known from the other settings. And takeaway is that the winter climate in Poland is strongly influenced by natural variability. And then the final part of this 1,000 years reconstruction series is to see how resilient was Lake Zabinskie ecosystem, and it was done based on the number of change points of this multi-proxy dataset. And if you look at the total change points per unit of time, you see that the closer to the present, there are more and more change points happening, and that's because once human impact on the lake became really high in the last centuries, Lake Zabinskie resiliency and buffering capacity was overcome by this human impact, and Lake Zabinskie became highly unstable. So yeah, that's a lot of that was caused by human activity, and it plays along with previous reconstructions. But also, the most recently, we came back to the short scale, to the last decade, six decades, and we used high resolution micro XRF and hyperspectral data in this part, in those 60 more or less years, where we have virtually no uncertainty in the chronology, but also we have meteorological data. And we see that the spring and summer temperature, as well as windiness during the ice-free period, can be used for calibration of climate proxies using only biogeochemical data, no paleoecological data. So using generalized additive models, GAMS, we reconstructed those two variables, and we see that the total carbon in the sediments as well as titanium could be used as predictors of the warm period temperature, with really good results in terms of statistics, while mass accumulation rates and silica abundance in the sediments could be used to predict number of windy days in the Lake Zabinskie. And that's how it looks when we look and plot the GAMS. So given that it is only two variables and they are purely geochemical variables, we have over 50% of deviance explained for temperature. That is, I think, that it's really good result. And also for the windiness, it's almost 50% of deviance explained. This seems to be really good. And that concludes the first part. The first part that for the last 1,000 years, we finished that with this conference that I don't know how many people are right now listening, but I think that some of you can find yourself on this picture. Some of us had a little bit more hair, and it seems to be very serious job what we are doing. And yeah, that is it for the first part. Then we are going to the second part, so that decade, which is about the data from the last decade, and it's currently submitted and under review. As you see from today, there is one review complete, so I'm feeling really anxious. We'll see what happens. So today I showed that a couple months ago on the conference, but maybe you didn't see it. So today I will show you what we submitted. So what motivates and drives us is that we still want to find the mechanistic explanation of links between the meteorology, lake water dynamics, and biochemical Varves formation in the Lake Zabinskie and overall. And for that, we asked three questions. First one is, can a reproducible pattern of relationships between meteorological conditions, limnological processes, and modern sedimentation be established? Then, do the surface sediment record the same variability of processes as the sediment traps? And finally, what kind of meteorological and limnological phenomena can we track with Varves? So that brings us to the lake observation or monitoring setup that we have in Lake Zabinskie since 2011. So we have two sediment traps located in the Hypolimnion of Lake Zabinskie. They are 1 meter above the sediment surface. One is retrieved every month. The second one is retrieved annually. And on this trap, we have mounted temperature loggers on 1, 5, 10, 12, 20, 30, and 40 meters. Then we also installed recently another line with the oxygen concentration loggers at 4 depths. So one is in the Epilimnion, 3 are in the Epilimnion, and one is in the Hypolimnion. And also every month and for some time, even every 2 weeks, we are measuring the water parameters using sonde. We measure water temperature, oxygen concentration, pH, total chlorophyll, A, conductivity, and so on and so on. We also collect the water samples for the major ion chemistry and biogenes and hardness, and obviously we measure water transparency. And also, not in scale, that's the deepest part of the Lake Zabinskie where we took course, obviously. So in the field, it happens to be, there are different times. Most of the time it seems to be really fine, especially during the season like right now. It's fun to go to the field, but sometimes despite the whatever is happening, we have to do the measurements. So it's on ice in the night. Even if our car breaks down, we are trying to be always there and not to miss anything happening in the lake water. So when we are talking about the weather and the sediment connectivity, we need to see what is happening in the weather, obviously. So one of the most striking parts of the climate of temperate zone is that obviously the winters are sub-zero temperatures occur in the winter, and then the summer can become pretty hot. But the difference is how long the winter is and how steep is the rise of the temperature after the winter season. And that changes from year to year in Lake Zabinskie. If you look at the precipitation data, it's not very promising. But then if we go to the wind speed again, it seems that the highest wind speeds occur only in winter, or mostly in winter, when there is ice on the lake. So the wind speed and wind fetch on the lake is blocked by the ice cover. However, throughout the other part of the year, the wind speed also has there are times when the wind speed is accelerating, and this gonna be really important later on. If you look at the modern limnology, so basically the extension of what Ala did previously, we see many more years that we tracked the changes in water column, and obviously there is recurring summer stratification. However, if you look closely every year during the summer, there is a drop of temperature for some time in the Hypolimnion. If you look at the dissolved oxygen concentrations, we indeed see that the lake is mixing in some years, either once or twice, and there are some years where anoxia in Hypolimnion especially is almost permanent, and it can span through 3 or 4 years. And anoxic boundary is reaching really high, close to the water surface. It's sometimes only 4 or 5 meters deep. And if you look at the water pH and chlorophyll A, basically they spike and rise rapidly after the ice breakout, when the algae blooms occur and the water temperature rise is changing the pH, affecting the pH. So due to magic of what we are doing in here, so we are continuously integrating the data. I can show you the most recent data. So it's from the last time we were in the field 1 month ago. And I just summarized how many times we're on Lake Zabinskie. It's at least 134 times we were there. We collected almost 100 sediment samples, a lot of water samples, and there was a lot of cable being put down and pulled up from the lake. And what is right now interesting, that the last 3 years, it seems that Lake Zabinskie tended to mix really effectively, which was not seen in previous years, not to that much, to that extent. So that's how the fresh sediment sample from the trap looks. Now it's in the bin. That's how water sampling looks. And here, so we have sediment trap samples from the decade, and we can look what is happening right now and see if there are some differences. So one of the important features is that every spring the calcite grains are obviously the biggest. Like it's normally the grading of the calcite size is that way, if it's normal grading. If we go to the summer calcite deposition, it's mostly micrate. So it's a very dense matrix of small calcite grains. Also in the summer, we often see abundant Phacotus algae, which are important sink of inorganic carbon. And during the winter, we see detrital sedimentation of whatever was in suspension during the time, and under the ice it can it can be deposited in a slow fashion. So if you look at the chemistry of the water, we can see that there is a every year there is some kind of seasonality. Every year under the ice, the pools of ions of calcium and biogenes are being replenished, and after the ice out and when the algae activity is becoming greater, there is these pools are being depleted, and this is seen especially for calcium as a deposition of total inorganic carbon in the sediment trap samples. So it's basically decalcification of epilimnetic waters. And what is also important is that calcium calcite deposition drives mass accumulation rates in Lake Zabinskie because it's a really dense material compared to the organic matter. And under the ice, mass accumulation rates tend to be really low, but mostly driven by the accumulation of organic matter. So we had the data from the last decade of the lake observation, and then we had to get the sediment core that would span exactly the same period. So we went there, collected yet another core from Lake Zabinskie. It has to be core like 100. It's core ZAP 2001/01. And what is for us important is that it was collected in the beginning of May, and we see that there is in the fin section that there is onset of calcite deposition that was seen also in the sediment trap material. So we have this intact sediment water interface. We obviously did slabs and we made fin sections. We subsampled this core, and that brought us to looking into the Varve sedimentology and microfacies analysis. So as it was said before, and it's proved right now, calcite layers are diagnostic trait and start of Varve here in Lake Zabinskie. However, but there are also multiple calcite layers that occur throughout the year, but they differ in terms of calcite grain size and development, and it's especially true for the spring layer, as you can see on the box plots. 2012, 2014, 2016, these are examples of years that were the complete turnover took place. And then the calcite in spring layer is great, and the biggest layers calcite grains are deposited, and they are developed in the best way possible, as you can see on the close-ups from the fin sections, like right here. So these are really nice grains being deposited in the sediments. And if you look in this very, in the year 2013, when the mixing was very short, it was took time for like 3 or 2 days. The calcite grains are very small and poorly developed. And then if you look to the transition from the fall of 2011 to spring of 2012, so in here in fin section, we see this transition from manganese-rich material to somewhere in here are diatoms, and then calcium-rich material. And then if we go to the spring of 2012, which was also intensive lake mixing, we see that calcite material goes into the manganese-rich material once again. Then we have some organic matter and diatoms, and then there would be another calcite layer deposited. And so in some selected years, there is a lot of manganese-enriched material, which we're interested in. So we took our fancy toys. We did geochemical mapping with Tornado XRF scanner, and we made geochemical maps of photopigments, so bacteriophyllophytin and total chloropigments. And you can see on those geochemical maps, especially for manganese, that the manganese deposition is highly incidental. So there is almost no manganese, and there are just layers full of this element, which is really striking feature of this, at least this part of the core. Later on, we'll be focusing on the profiles which were extracted from those maps because they are easier to interpret and they make time series. So we compared these profiles from XRF and hyperspectral scanning with our microphages analysis and the scheme of sedimentation. So we see that indeed calcium tracks multiple calcite deposition in spring and summer. We see multiple peaks. Phosphorus co-precipitates with calcium, while the trital elements such as potassium, titanium, and partially iron track mineral deposition, especially close to the Varve year end, meaning basically winter. However, part of the iron is bound to sulfur, or sulfur is bound to iron, so it makes it like an intermediate element. Manganese is, as I said, highly incidental, and it should track oxidation events. Bacteriophyllophytin A tracks mostly summer stratification, but it's not that easy to interpret because bacteria that are producing this byproduct, this pigment, need anoxic waters, but also they have to be in the photic zone, and in Lake Zabinskie the water transparency is really bad, especially in the summer. Sometimes it's only 80 centimeters. And then we have total chloropigments A and silica, which track mostly algae bloom and deposition in the sediments. Also, we did, like it's very often done, principal component analysis on those biogeochemical data to see what are the main modes of change for those variables. And we indeed see that the calcium and phosphorus are driven by the same variability. There is manganese somewhere in between the position of those elements and indicators of algae blooms. And then on the other side of the axis, we see this cascade of detrital through intermediate, through redox-driven anoxic sulfur species, and then bacteriophyllophytin A showing summer stratification. So PC1 basically shows either stratification, summer and winter, or mixing periods in Lake Zabinskie. And having that data, we are still not sure, so we went extra mile and selected material from the lakes that we thought that should correspond to holomixes, and in this and to years that were meromictic, and we did powder X-ray diffraction analysis on those samples, and in years that were holomictic, we see that there is rhodochrosite, so manganese carbonate, which constitutes up to 10% of mineral composition. However, in the years that we deem to be meromictic, there is virtually no manganese material also in XRD analysis. So having all of that together, we can use the proxy data, the geochemical data from the trap, to fix in time our proxies from the sediments. So basically we try and look and find the same patterns in geochemical data from the trap material. If there are similar patterns in the material from the core, there is indeed. And if you find the same patterns, then you can, by this cascade, you can fix the peaks from XRF data to peaks in sediment trap data, and then you can fix that to the meteorological data, because sediment trap and meteorology are resolved in calendar days, in fact. So for total inorganic carbon, we use that as an anchor for calcium record. And for manganese, we used oxygen concentrations in the hypolimnion and holomixes in fall and spring events. And we also fixed those layers into the calendar scale. And having done all of that, we can go to the comparison and synthesis of our results. So we compare atmosphere, hydrosphere, meaning lake water, and lithosphere, sediment trap data, and sediment core. And we see that mixing means in Lake Zabinskie means obviously replenishing of the oxygen in the hypolimnion, but also it's a oxycline migration, meaning that the manganese is being geochemically focused in the deepest points of the lake. And ultimately, the presence of oxygen also can lead to the burial of manganese in the sediments and its preservation. Also, mixing means that the internal biogen loadings from the hypolimnion are increased. That means that the blooms in the epilimnion are more and more intensive, and that leads to the high calcite precipitation from the Hypolimnion. However, obviously temperature change means easier calcite precipitation from the Hypolimnion, and this relationship is important throughout the stratification when the rapid increase of windiness means shallow mixing in the Hypolimnion and metalimnion of the Lake Zabinskie, replenishing calcium pool in those shallow strata, but also temperature drop and then subsequent very fast temperature rise in the Hypolimnion, leading to the quick changes in inorganic carbon complex buffering capacity and leading to the next precipitation events. So we can trace those events, I would say mechanistically up to compare it to week-long scale in the meteorological data. So with all of that, we also see that the sediment trap mass accumulation rates in the sediment trap and in the sediment core tend to show similar cores. It's not always the same, but more or less they show pretty much close pictures. So that leads us to the conclusion and hopefully answers to our research questions. We see that there is a direct relationship between meteorological conditions, limnological processes, and modern sedimentation in Lake Zabinskie. Especially air temperature and wind speed affect parameters of the water column and also primary production, and ultimately they govern the sedimentation in Lake Zabinskie. So to answer the research questions, for the first one, we can say that the combination of meteorological data and lake monitoring data, the composition of sediment trap samples and sediment core analysis enabled us to identify influences of meteorological conditions on the sediment formation in our lake. For the research question 2, variability in mass accumulation rates and sediment composition, which was observed in sediment traps samples, is well reproduced in the sediment record. Therefore, good preservation of major environmental signals makes this sediment archive a reliable source of information for next and paleoenvironmental reconstructions. And finally, in Lake Zabinskie, grain size of the first, meaning spring calcite laminae, is positively related to the intensity of spring mixing, while next every second and third calcite laminae inform us about colder and more windy periods, followed by a rapid increase of temperature during the summer stratification. And furthermore, manganese peaks are highly incidental and correspond perfectly with oxygenation of the Hypolimnion and sediments and holomixing events. So that means that the manganese, at least in Lake Zabinskie in this setting, is an excellent recorder of the deep mixing events of this site. And holomixes changes and is driven mostly by long and cold springs or long fall and late formation of ice cover on the lake. So is that the end? No, there is something going on in the future, meaning that we are going back to the past and back again to climate, but not only. So what Paul recently showed in Agadir on OSM, that there is a possibility for calcium-titanium ratio-based reconstruction of warm season temperature over the entire Holocene. So this is in works, but also works on modern phytoplankton responses to weather changes, meaning diatoms and chrysophytes. And we started second decade of Lake Zabinskie observation, so it's never going to end, I think. So thank you for your attention. That's all. I think it took me a lot of time, but I hope it was worth it. And